Let's get ready to do some math. Okay, back again, advanced placement calculus, AP review going on. Okay, let's do XVA day 2. That's what we're working on here. Hope you tried your homework problems with the calculator. Hopefully not too terrible. The 2005B problem right here. Give you velocity. They want acceleration with the calculator. That's a piece of cake. Where the particle changes direction. Don't forget about that justification. The particle moving left here because velocity is negative. Make sure you could do these things. That should have been pretty easy. Position at t equals 2, just like stuff we talked about last lesson. Average speed of the particle is kind of strange. You won't have to worry about this on the AP because the average value function is not there. The average value equation formula. But they want the average speed. They want the average value of the speed function. Okay, the speed function is the absolute value of velocity. We talked about that last lesson. If you want the average y value of the speed function, plug it into 1 over b minus a, integral from a to b of whatever the heck you want the average value of. Okay, so that's the average value formula right there. So that might have tripped you up a little bit, but even if it did, if you didn't do part D, you got 7 points out of 9. Everyone in this class should be able to do A, B, and C. I don't care what your grades have been like all year. Everybody can do it, but not everybody on the AP, and that's why you can do a good job on your AP exam. 2011, more recent. Was anything weird? Let's see. They give you velocity. They give you acceleration. Kind of cool. Initial position. Speed increasing or decreasing. We talked about that. Average velocity. Remember what we used to say? Do you use velocity for average velocity? No, you use position because it's the average rate of change of position. Thing is, they didn't give us the position function. But if you want to think about the average rate of change of position, remember velocity represents the rate of change of position. If you want the average y value of velocity, you'd use the average value formula on velocity. Once again, if it freaks you out a little bit, try not to worry because it's not on your AP, but if you see just the word average, try to think average value formula. If you see average rate of change, try to think the average rate of change formula. They're interchangeable many times. Sometimes you have to use one over the other and it can be difficult, but usually those are the harder types of problems anyway. I wouldn't worry about it. Part C is the joke of the year. Total distance traveled, integral absolute value of velocity. And seriously, part D, the particle changes direction only once. You got to find where it changes direction. Make sure you say y, velocity equals 0, velocity changes sign. Then you should be able to figure out position there. All in all, this is another possible 9 out of 9. Maybe you only got 6 out of 9 because part B bothered you a little bit, but you won't really see that on your AP. Let's put those calcs away and do some problems without a calculator here. Let's go to 2009 Form B. Number 6, okay, no calculator. You see that now we're given velocity again. They love to give you velocity, only not algebraically this time. It's represented tably, which really means numerically. The velocity of a particle moving along the x-axis is modeled by differentiable function v, where position x is measured in meters and time t is measured in seconds. So they don't even give you the position function. They tell you it's in meters. They give you velocity in meters per second. Time is in seconds. Velocity is differentiable. A lot of people just gloss over that. That's important. That means that there's nothing weird going on. It's continuous also, so you can evaluate integrals and stuff like that. Selected values of v of t given in the table above, and then it looks like they give us an initial position, okay? Part A, which is a part A, is huge, okay? There's a great chance of you seeing this on the AP exam. Certainly a table question like this. We'll do a whole review on tables, very popular problems. I think you might see one. Estimate the acceleration at t equals 36. Show the computations that lead to your answer. Indicate units of measure, okay? So estimate the particle, the acceleration of the particle at t equals 6. So A of, 36. So A of 36. You know, we don't want to know what A of 36 is equal to, which is good. They didn't give us an acceleration function. We can't even come up with one, right? Because they didn't give us a velocity function. They just gave us selected values. But they did give us velocity. Remember that you take the derivative velocity to get acceleration. So A of 36 is the same thing as V prime of 36. And this is an instantaneous rate of change. There's only one way to approximate an instantaneous rate of change in this class, and that's using average rate of change, okay? So if you want to get the instantaneous rate of change at t equals 36, remember t equals 36 is kind of right here, right? In between the 32 and the 40. Get average rate of change. Move a little bit to the left, and we'll move a little bit to the right. We did this earlier in the year, okay? And it's something you should know how to do. If you want to estimate instantaneous rate of change, use average rate of change. You could even use the 36. They don't give it to you, but if they gave you 36, you could use that point of tangency and go a little bit to the right, or use that point of tangency and go a little bit to the left. We try to go the same distance left and right, not too big of a distance if possible. So here we could do average rate of change of V from 32 to 40. So that's V of 40 minus V of 32 over 40 minus 32. I think of my answers, I didn't write this part. I went right to what you're computing. Write this part. They want to see that, okay? That's actually important. I got to change up that answer key. V of 40 we know is going to be equal to 7 minus V of 32, which is negative 4 over 8. So what do we get? Negative 11 over 8. And you want units here. Remember, we're approximating an acceleration. If velocity is in meters per second, that means acceleration is in meters per second squared. Okay, so actually a pretty doable problem there in part A, and you'll see that often. Remember, if you want to approximate instantaneous rate of change, use average rate of change. We did that earlier in the year. Using correct units, now they want you to explain the meaning of the integral from 20 to 40 of V of t with respect to t. Then they actually want you to use a trapezoidal sum with the 3 subintervals indicated by the data in the table to approximate this integral. You can approximate the integral first if you want to, and then you could actually use correct units and explain the meaning. I'll approximate it first just to do it that way. Trapezoidal sum, and you're like, oh, trapezoidal rule, start with the 1/2 delta x, and start with f of the lower bound and with f of the upper bound. In between, put 2's in front. No, you can't do an expansion here. 3 subintervals indicated by the data in the table. They did not say using 3 subintervals of equal length. So we go from 20 to 40, 3 subintervals. The first one is 20 to 25, then 25 to 32. That's the second one. And then 32 to 40. That would be the third one. So really you just need to get the actual area of a trapezoid. You got to get area of each of these trapezoids separately. Remember, the area of a trapezoid, you're always going to say area is equal to 1/2. Then we like to say b sub 1 plus b sub 2 times the height. Okay, just remember these trapezoids will look like this or something like that. So the height is actually delta x right there, the change in x, and the 2 bases are really f ofs because they really represent y values, or v ofs in this case right here. So that first trapezoid, you can start with 1/2 because it's in the trapezoid formula. b1 plus b2, well, the first trapezoid goes from 20 to 25, so v of 20 plus v of 25. And then the height is just going to be your delta t in this case, okay, which is just going to be 20 to 25, which is 5, okay? And that right there, that's the area of the first trapezoid. And it's been a little while since we did this, okay, but you should be able to go back into the groove. The area of the second trapezoid, 1/2. Second one goes from 25 to 32, so you want 2 v ofs here, okay, so v of 25 plus v of 32. Times his height, which is really his delta t, which in this case is equal to what, 7? Okay, and that one right there, slightly cut off from what you can see, but there's my 7. Then I'll put a little plus sign here, and then we'll do the last one. I'll squeeze it over here. We'll do 1/2. This one goes from 32 to 40, so v of 32 plus v, of 40, and that delta t is going to be 8 right there. So they want to see that right there, that you could do the actual expansion, even though it's not a perfect expansion here. Here you got to calculate the area separately. But then plug in numbers. 1/2 v of 20 is going to be negative 10, plus v of 25, negative 8, and then times 5, plus 1/2. And now we have v of 25, which is negative 8, plus v of 32, which is negative 4, times 7. And then plus finally, we're going to have 1/2. V of 32 is going to be negative 4, plus v of 40 is 7 times 8. And that thing right there, really nasty looking. Box it in, okay? That's all you need right there. My homework solution, I get that the answer is negative 75, which is great, okay? But remember, you don't need to simplify things on the AP. Please, don't simplify them on your AP, okay? You don't need to compute these things. They want to know what this represents, okay? Remember, whenever you explain a definite integral, unless there's an absolute value sign in here or a fraction out front. If there's an absolute value sign here, then you're looking for, like a total distance traveled. If there's a fraction in front, then it actually represents the average value of something. But look, if you don't see either of those things, when you talk about definite integral, you always want to say the change in. People like, change in what? change in whatever the heck you just integrated the derivative of. And we just integrated velocity. That's the derivative position, the rate at which velocity changes. So if you integrate the rate at which position changes, is velocity. So if you integrate the rate at which position changes, you get the change in position of, what was this, a particle, of the particle. So just like we did yesterday, but now I got to put units, right, in meters. Position's going to be in meters. And then don't forget to say from t equals 20 to t equals 40, and that would be in seconds, okay? So whenever you describe a definite integral, always two units to worry about, the units for the answer and the units for the bounds, okay? So that is something to be careful of. And B isn't as bad as you might think. It's AP review. It takes a while for you to get used to this stuff, but eventually you'll hopefully get into a pretty decent groove. Okay, so B is really not too terrible. I know it's really annoying calculating a trapezoidal sum without the expansion. Very, very popular on the AP exam. Could easily be on your shortened AP exam this year. Part C is pretty easy. From 0 to 40, which is what they give you the information about in the table. Must the particle change direction in any of the subintervals indicated by the data in the table? These are our subintervals up here. Okay, we got 1, 2, 3, 4, 5 subintervals. In any of the subintervals indicated by the data in the table, must the particle change direction? If so, identify the subintervals and explain your reasoning. If not, explain why not. Remember, we know a particle is going to change direction when its velocity equals 0 or it's undefined, which they don't tell you here. They never tell you where velocity is 0 or where it's undefined. But really, you also know you change direction when velocity changes sign. And you could see from 8 to 20 here, velocity changed sign somewhere in that interval. It went from positive to negative from 8 to 20. So I know from 8 to 20, the particle must change direction. And then I know from 32 to 40, the velocity changes from negative to positive. So that means the particle must also change direction. So that was 32 to 40. So we can say particle must change direction on these intervals. Particle must change direction on these intervals because, and we could say because velocity v of t changes sign. You don't even have to say that it equals 0 or is non-existent. You don't know which it is, okay, but it has to be one of those if velocity is actually going to change sign. So part C, really not that bad, which sets up part D, which is a nightmare, okay? So if you need to pause this thing or just skip ahead to the next question, there's nothing wrong with that, but I'd like you to try, okay? They love to do this. Sometimes they give you a whole part 2 problem that's a real horrific monster. People average like 1.6 points out of the 9 on it. Sometimes they give you a problem where A, B, C, and D are not bad. A, B, and C are not bad, which they weren't in this problem. Then D is a disaster. Sometimes they give you a problem where A, B, and D are easy, but C is a nightmare. So look, if you see something that's a nightmare on a problem, doesn't mean the next part is difficult. D here is difficult. If you can't get it, no big deal, okay? But they say, suppose that the acceleration of the particle is positive. So acceleration is positive from 0 up to 8 seconds. Explain why the position of the particle at t equals 8 seconds must be greater than 30, okay, 30 meters. And people are like, what the heck are you talking about? Well, if you get the position at t equals 8, which you can't really do, but think about it. As long as we have an initial position, which we do, they told us what x of 0 is equal to. They told us it was 7. So remember, if you want position at t equals 8, use position at t equals 0 and say, hey, what the heck was the change in position from t equals 0 to t equals 8? Integrate the rate at which position changes. And that's going to tell you that x of 8 is really equal to x of 0 is what, 7? Plus the integral, we'll say from 0 to 8 of v of t with respect to t. And they want you to show that this position right here has to be greater than 30 meters. So our position right here, that's 7 plus the integral from 0 to 8 of v of t with respect to t, has to be greater than 30. All right, you're like, what the heck do I do here? Well, the first thing is you just subtract 7 from both sides quite easily. You get the integral from 0 to 8 of v of t with respect to t is greater than 23, which would be great if you had like a graph or something. Then you could actually, calculate this area or show that the area has to be positive for some reason. That doesn't happen here, but you could try to make a little bit of a graph of v of t. Here's where things get real snark. Like, it's not too terrible to get right there. You could do it. Here's t, here's v of t. And we're only going from 0 to 8 here, you might notice. Okay, it said so up here. The acceleration is positive from 0 to 8, and at t equals 8 seconds, okay? You know, and we also know we're integrating from 0 to 8 right here. So if you actually graph 0, 3, that's a point, right? So this is the point 0, 3. And then at 8, we have 8, 5. So say that's the point right here, 8, 5. And look, we don't know what's happening with this velocity function. We don't know how to graph it, but believe it or not, we know some things because they told us acceleration was positive. Why would they tell us acceleration is positive? That means the derivative velocity is positive. That means velocity is increasing. So v of t is increasing. So look, I have no idea what the function looks like, but I know it increases to get from this point to this point, and I know it's not going to decrease anywhere in between. And now they want you to show that this integral has to be greater than 23. Well, here's the interesting thing. Suppose the function remained constant. It didn't even increase. Suppose it did that, right? Just went from there to there. Then you can get the area quite easily. This area would be equal to, you know, this height is going to be 3 right here. This distance right here is going to be 8. So the area is 24. So check that out. The integral from 0 to 8 would be greater than 23 even if velocity wasn't increasing, okay? Even if velocity remained constant. So obviously if velocity is increasing, then the integral is going to be greater than 23. So we could even write that out. It's not so easy. How do you even write this? We're going to say even if v of t remained constant, then the integral from 0 to 8 of v of t with respect to t would be equal to 24. So we could say since v of t is increasing, since, how about this? Since a is greater than 0, that implies v of t is increasing, which you don't really need to write because we had that written over here. We're going to say thus the integral from 0 to 8 of v of t with respect to t has to be greater than 23 because it's going to be greater than 24. It's greater than 23 even if this thing remains constant. So I don't know if you understood that or not. I know there are people out there who definitely understood what I just wrote down. Other people are like throwing things at the wall right now. What are you doing to me, Berto? Forget about part D. Seriously, okay? Part D was worth 2 points. If you can get the 7 points before part D right there, you're doing so amazingly well, like really, okay? So, you know, just remember stuff like that when you do AP review. There's going to be nasty, funky stuff. Chalk it up as an L. Let it roll right off your shoulders. Do not let it bother you, okay? Let's go to 2005, and now instead of velocity being represented with a table or an algebraic expression, velocity is now represented with a graph. Very popular problem. I think I said yesterday we could do an acceleration one. I decided against that. We'll get back to it when we need to. I thought this was a better problem here, even though there's a lot of stuff I have to clean up on this paper. My OCD is kicking in. I don't like all these little dots. Get some whiteout going. Anyway, so now we got a car. Meep, meep, is traveling on a straight road for 0 to 24 seconds. They give you the car's velocity in meters per second, modeled by the piecewise linear function defined by the graph above. So this is a piecewise linear, 3 line segments. Part A, which is a part A, should be a piece of cake. We want the integral from 0 to 24 of v of t with respect to t. Then using correct units, explain what it means. We just did something like this last problem, only we had to calculate this definite integral. We had to approximate it using a Riemann sum expansion. It wasn't even a Riemann sum expansion. It was a trapezoidal sum expansion, and we had to calculate the areas separately. Here, this is just the area between v of t and the t-axis from 0 to 24. We could calculate this area. It's a trapezoid. You could use the formula for the area of a trapezoid. And even though it's required for the AP curriculum, none of you will. You'll break this down into 2 right triangles and a rectangle. Nothing wrong with that. Okay, this right triangle right here has base of 4, height of 20. 1/2 times 4 times 20 is 2 times 20, which is 40 right there. Hopefully not your test grade, unless it's on the AP, because then it's a 3. Here, from 4 to 16, that's 12. This is a rectangle. 12 times 20 is going to be, what, 240 for the area. And this base down here is 8. 8 times 1/2 times 8 times 20. 4 times 20 is going to be 80 right there. So really, this integral right here is 40 plus 240 plus 80, which, by the way, you could box in. You don't actually need to add those things up right there and get what, 360 is what it would be. Okay, so you could leave it that way. But look, they're going to want you to use correct units. Explain the meaning of the integral. Remember, if you integrate velocity, velocity is the rate at which position changes. You get the change in position. I don't think you have to worry about that on the AP, but you might have to integrate the rate at which snow is falling from the ground, and then you'll find out the actual change in the amount of snow that fell on the ground. Okay, you're going to have to do stuff like that. We'll see it soon enough. We're going to say change in position of the car, units in position would be in meters here. Then we're going to say from t equals 0 to t equals 24. And this was seconds right there. So make sure you kind of get used to explaining a definite integral. Try to start with the phrase change in. Moving over to part B. Kind of cool right here for each of v prime of 4 and v prime of 20. So that's the derivative velocity. It's really acceleration. Find the value, explain why it does not exist, indicate units of measure. Well, if you try to do v prime of 4, that's the slope of the line tangent to the velocity graph at t equals 4. And you can see at t equals 4, there's no slope right here, okay? This is a sharp point. The slope coming in from the left does not match up with the slope coming in from the right, so that does not exist. You know, they say explain why it does not exist if it does not exist. If you just say because it's a sharp point, you might be all right, okay? What's really happening with a function not being differentiable is that means the slope coming in from the left of 4 is not equal to the slope coming in from the right of 4. So that means the slope that velocity is approaching as t approaches 4 from the left-hand side. So the limit as t approaches 4 from the left-hand side of the slope of velocity, which is v prime of t, is not equal to the limit as t approaches 4 from the right-hand side of the slope of velocity. Technically, that's what they want you to write up. If you struggle with that a little bit, I understand. If you put because it's a sharp point, you still might be all right with points, but be careful. Technically, this is what they want. V prime of 20 is probably easier. You know, here it's the slope of the line tangent to the graph of v at t equals 20. Here's the point of tangency. You could try drawing the tangent line to the graph at t equals 20, but you can't draw the tangent line. You just end up redrawing the function, which is good. That means it's a linear. It has a constant slope. So the slope at t equals 20 is going to be the same as the slope anywhere from t equals 16 to t equals 24. Here, to get instantaneous rate of change, we could use average rate of change. We're not approximating instantaneous rate of change. There's no difference for a linear between the instantaneous rate of change and the average rate of change. So I just want the slope from the point 16, 20 to the point 24, 0. It's this point right here. So 0 minus 20 over 24 minus 16, 0 minus 20 over 24 minus 16. And look, you don't have to calculate what that's equal to. You could just box it in right there. Do they want appropriate units here? Yeah, indicate units of measure. We couldn't do it in the last problem because it was non-existent. But remember, we're getting the slope of velocity. We're getting acceleration. So velocity is in meters per second. Acceleration is going to be in meters per second squared. Okay, so just be careful with stuff like that. Hopefully not too terrible. I think pretty doable right there as far as part B is concerned. Everybody freaks out about part C. It's really easy. Let A of t be the car's acceleration at time t in meters per second. That's meters per second squared. From 0 to 24, they want you to write a piecewise defined function for A of t. And people are like, oh, a piecewise defined function? I can't do that. Yes, you can. Search your feelings. You know it to be true. Okay, and look, the idea is that it's a piecewise function, A of t, because velocity has 3 pieces, and acceleration is the slope of velocity. All you need to do is figure out this slope, and this slope. Those are your 3 acceleration functions. So acceleration is going to be the slope of velocity. From 0 to 4, rise over run. The rise is 20. The run is 4, so 20 over 4. Positive 20 over 4 is the slope. And that's going to occur from 0 up to 4. Don't include 0, and certainly don't include 4. We can't include 4 because we know acceleration doesn't exist at t equals 4. We talked about that before. 0, they never want you to consider derivative at an endpoint on the AP exam. So you can either include it or not include it. It's up to you. It won't make a difference. The slope from 4 to 16 is great. It's equal to 0. So acceleration is equal to 0. Starting at 4 but not equal to 4. Ending at 16 but not equal to 16, because that's another sharp point at 16. The slope of velocity doesn't exist at 4 and 16, hence the acceleration doesn't exist at 4 and at 16. And that final slope, down 20 to the right 8, so negative 20 over 8, and that's going to be from 16 up to 24. So it's actually really, really easy here. And if you could do A, B, and C, You already got 7 points. There's a lot of points to this problem right here. Don't be freaked out about this. There's one on homework, which I think is going to be pretty tricky, okay? There's a few homework problems. Do the best you can with them, okay? Remember, it's all about earning points here, not getting every point. You'll start to see the same types of questions and one question to another. Those are the ones you want to start to get used to. Part D is 2 parts. Find the average rate of change of V over the interval 8 to 20. Does the mean value theorem, guarantee a value of C from 8 to 20 such that V prime of C is equal to this average rate of change? Why or why not? Slow things down. The first thing they want is the average rate of change of V over the interval 8 to 20. Remember, if you want the average rate of change of a function and they give you that function, use f of b minus f of a over b minus a. So the average rate of change of v would be v of b minus v of a over b minus a, or in this case, v of 20 minus v of 8 over 20 minus 8. Okay, they want you to calculate that right there. So we know that v of 20, and here's something that's kind of cute. V of 20, you're like, wait, what the heck is it equal to? If I plug a 20 into this thing, remember, this is a non-calculator problem, so you can guesstimate that v of 20 is equal to 10. You know, technically what you're supposed to do is you're supposed to figure out what the equation of this line is right here. We know the slope is negative 20 over 8. I'll put a t right here. Plus the y-intercept. You got to figure out what the y-intercept is. Plug in the y equals mx plus b. Replace everything but the b. It's going to have a positive y-intercept, yada, yada, yada. You could plug into that thing, that 20, to show you that v is equal to 10. Don't waste time on that, though, okay? This is a time waster. If it was a calculator problem, maybe it's 10.01 or something like that. But you can guesstimate without the calculator. V of 20 looks like 10, so I'm just going to go with 10. Even if it's wrong, you don't want to waste all the time calculating this, okay? It's better to have a wrong answer, okay? But you have everything else set up correctly. Mine is v of 8. V of 8 is 20. That's easy to see. I'll leave it as over 20 minus 8 because dang the squirrels, okay? I'm going to leave it set up this way. We don't need to actually simplify this right here. It is average rate of change of velocity. Rate of change of velocity is acceleration, so it's meters per second squared. So that's very doable, and that gives you a point, and that's 8 out of 9 right there. But then it says, does the mean value theorem guarantee a value of C from 8 to 20 such that V prime of C is equal to this average rate of change? Remember, we got the average rate of change from 8 to 20, and the average rate of change of a function of V in this case is the slope of the secant line from t equals 8 to t equals 20 right here. It's the slope of that line. Now they're asking, does the mean value theorem guarantee a value of C such that V prime of C is equal to the slope of this line? And V prime of C represents the slope of a line tangent to the velocity function. Remember what the mean value theorem says? It says if a function is continuous and differentiable, there has to be at least one x value C, or t value in this case, such that the slope of the secant line is equal to the slope of the tangent line. There had to be a place where the slope of the tangent line is equal to the slope of the secant line. Those two lines are parallel. That's not true here. Here the slope is 0. And here the slope is negative 20 over 8. The slope never becomes this other value right here of negative 10 over 12 that you could have calculated if you wanted to. And the reason the mean value theorem doesn't guarantee it is, remember, the mean value theorem only guarantees a place where the tangent line is parallel to the secant line if the function is continuous and differentiable. And you can see for sure that velocity is continuous, but it is not differentiable at t equals 16. So mean value theorem does not guarantee said value, does not guarantee said value, because, and v of t is not differentiable at, we'll say t equals 16. Make sure you say where, don't just say it's not differentiable, okay? So the mean value theorem does not guarantee that value because v of t is not differentiable at t equals 16. So the mean value theorem creeping his way into the problem, okay? You know, something that you'll see in these AP problems, they kind of throw everything together and mix it up in a beautiful symphony with beautiful harmonies and great drum beats and all that good stuff. Anyway, do the best you can. Think about gaining points. Probably some pretty tricky homework tonight. Do the best you can over the weekend. Have a good weekend. I hope you're all safe and healthy. That's the most important thing. Don't be worrying about grades right now and freaking out. You have so many things on your mind. Just do the best you can, but put in the work. Don't just sit there and do nothing. Unless you have things going on that are more important than mathematics. And I understand that. I really do, okay? But if you don't, please put in the work, and you could really do well on this thing. You might have a chance to do better on this AP than you initially thought. Who knows what they're going to do with this AP, and they're probably going to be more friendly with these grades than they have been in the past. I mean, we have some serious stuff going on in the world right now, so take advantage if you can. I'll have a take-home assignment coming out to you at some point. Will it be tonight? I don't know. I want to say I don't think so, but I guess we'll see how the cookie crumbles. Anyway, have a pleasant weekend. This is Berto signing off. Adios.